All right, so today will be the second last Q&A session for the semester, and you can expect one more set of lecture video to be released at the usual time next Wednesday. And for this week, I got the final 30 minutes of the lecture video to be released, hopefully later this afternoon, just to finish the initial model for our second case study. And then let's go over some announcement here. And we got our lecture week 11 release. That's a new case study about distributed program, about FTP. And the idea would be we talk about the initial model for this week, and then I'll talk about at least the first two refinements for that distributed program. And that'll be it for the course. And for your written test number 4, it will be the final test next month, next Tuesday, right? The usual time. There should be no surprise to the format and also the time. For your lab number 2, of course, your expected completion date will be April 11th. But I think maybe next week we should really talk about it, right? There might be certain parts I can give you some guidance so you can have more focused study about lab number 2. It's definitely covered in the exam. Do you guys have any questions related to the course about the course in general before I talk about the Google Doc questions? Anyone? You can speak up or you can put on the chat. All right, everybody's happy, clear about what's going to happen? Alrighty, let's now move on to Google Doc. I got 4 questions in total, but I think they're mainly just the clarification about the second refinement, specifically for the bridge controller. Okay. The first one over here is just about the ML pass and IL pass variables. Remember, we introduced these two variables for regulating the traffic lights so that we don't have any divergence in the second refinements. And your fellow student was really wondering about the init events is supposed to initialize. They use the word establish. I suppose they really meant initialize. The init event is supposed to initialize the two variables, and I explained that they should be 1, right? And let me just go a little bit further about why they should be 1, cannot be 0. And your fellow student was really wondering about what if the init event does not really try to establish them? Doesn't that mean their value can be arbitrary? Yes, that's correct. If you don't actually try to initialize these two variables, that means their value can be, each one of them can be either 0 or 1. However, if you allowed that non-determinism, in that case, you're going to run into issue when you try to prove it, right? Let me show to you why. When you try to do 1 and 1, for example, initially, and you can see for the very first occurrence of the new events over here, and remember the variant expression that we introduced earlier. So the variance, let me just remind you over here, that we used was ML pass plus IL pass. Right? If you think about its initial value over here, the variant value is simply 1 plus 1, which will be 2. And then after the occurrence of the new events over here, you can see the variant value is strictly decreasing because 0 plus 1 is actually 1, strictly less than 2. So that one there is actually okay. So that's why having these two initial value being 1 is actually a acceptable choice. What if we allow any arbitrary value for the initialization, which is what your fellow student was asking? The answer is you may not be able to prove about the strictly decreasing property, the proof obligation for the variant. Remember, there are 2 proof obligations for the variants. I'm talking about one of them. So let's say, hypothetically, say the init events does not initialize the ML pass and IL pass. In that case, they could be arbitrary. So there are 4 different combinations, right? You can each one of them can be 0, 1. Let's say we simply try this one here. Let's say we initialize them to be, let's say, ML pass and also IL pass. What if I simply initialize them to be, let's say, 0 and 0, right? In that case, it's going to be problematic because what we do is MLTL green is actually not going to, let me just make it more precise for you. So after MLTL green, we know that it's only going to assign 1 it's only going to assign 0 to ML pass. In that case, after this, ML pass is going to remain to be 0. And also the IL pass, it wouldn't change it. So it will still remain to be 0. So you can see the variant value here is going from 0 as the sum to also 0. So it's not strictly decreasing. So that's actually not acceptable. Right? So that's why this combination here should be the way to go. Is it safe to assume that the init events for M2 initializes IL pass and to 1? Yes, correct. I think that's kind of obvious from the context for our lecture. I just didn't really define that init events, but that should be obvious in the context. That's correct. All right, any follow-up to this? Anyone? Everything clear? All right, hearing none, seeing none on the chat, let's now move on to the second one. Okay. The second one here, I think I like the second question. The second question was really about when we try to, let's say, formulate the proof obligation, especially for relative de la freedom for M2. Okay, let's now just take a look at that. The way we put the invariance as a hypothesis, it is true we have to accumulate the invariance from model 0, from model 1, and from model 2. Basically, all the models that have been constructed so far. That's why we want to accumulate them. And the question was, however, when we try to put the disjunction of the guards, why are we not accumulating the guards as well? So this is only the abstract guard from M2 for all the events. But why don't we also accumulate the guard for the earlier model? It's a good question here, and the answer is we shouldn't. The reason is when we talk about abstract guards and when we talk about invariance, there are different categories of the artifacts in the model. And for this relative de la freedom over here, we want to prove the relative de la freedom specific to M2 only. So that's why you should only put the abstract guard specific to M2 here only. On the other hand, when we talk about invariance, so these are the safety properties that should be held across the models. That's why they should be put as the hypothesis over here. Right? Let me just make a quick point over here. For all the invariants over here, so these are more like a safety property. Meaning that they should be used. Used is not a good word. Should be preserved. Meaning that you can use them as hypotheses across models. M0, M1, and M2. That's point number 1. And for point number 2, over here, so this one here is just about the abstract guards. For proving the relative de la freedom of M2 only. That's why you don't really include the abstract guards for other earlier models, the more abstract model, for M2 only. Right, that's a quick clarification for this. Any follow-up you guys are wondering? Anyone? I hope that makes sense. All right. Hearing none, let's now move on to the next one. Okay. This one here is really about the splitting of the events, right? So you can definitely read over your fellow students' question there. I think it's rather clear, but let's now take a look at the actual my actual response. Let's take a look at the ML out events, right? Remember we said ML out 1 and ML out 2. And if you recall what's really happening in the original ML out, the original ML out goes like this. We actually got the when. Over there, we don't have the case analysis on the condition for a plus b plus 1. We only got ML TL equals green, and also we got the action there only about a becomes a plus 1, and we don't have that turning the traffic light to be red, right? That's only available when we try to split the events. As to why we actually want to turn the traffic light to be red, you can refer to the explanation back in the lecture video. I explained that very thoroughly over there. You can refer to it. So I'm not going to repeat here. If you look at the original guard over here, you can see we are trying to keep this one here still. We still got this, we still got this. But we actually got some extra guards. It looks like extra, but it turns out logically, they are not really extra. Not really, okay? Let me show to you. And I really summarized that over here, right? Let's say, hypothetically, if you actually want to, let me just tell you the correct one, and then I will tell you why the proposed one is actually not that correct. If you look at this guard over here, and also this guard over here, we are basically saying, given that MLTL is actually green, we may either let MLR1 to occur, or we may let MLR2 to occur, either one, right? So let's disjoin the guards together. If you try to disjoin the guards, it's going to be, let's say, disjunction of the guards of ML out 1 and ML out 2, right? Let's look at the disjunction over here. It's going to be A plus B plus 1. Oh, let me just write it more precisely. Let me try to put it in, let me put some label so they can save some writing. Let's say this part here, MLTL green. Also here, MLTL green, the same. Can we just say it's actually P? And we got A plus B plus 1, not equal to D. Can we just say it is Q? And this one here, it is equal to D. So exactly the negation. So this will be not Q. Right? Let's use a label. So what we have is, for MLR1 is P and Q. Or, right, we'll talk about disjunction. The guard for MLR2 would be P and not Q. And what is that equivalent to? I'll leave the proof to you, but you can easily use the distributivity of the disjunction. Right? If you do that, it's going to be equivalent to just true. This nicely justifies about the splitting nature of these two events. You're basically saying that you try to split the original ML out, given that MLTL is green, into two cases. And we are not going to miss any cases. Either it's going to be this or not this. P or not P is equivalent to true. So that's why we are not missing any cases. That's from the design point of view. If you actually try to do what your fellow student proposed, to say less than D and also equal to D, logically speaking, you are missing one case, which is when it is larger than D. Of course, you may argue that how can we ever actually get to the case where it's actually larger than D? But logically speaking, it's just not complete. So I think in terms of the proof, you want to make sure your guard can also also can facilitate your proof. So that's why having not equal to is actually the better way to do it. That's one justification for why we want to use the not equal to. Another one which I want to point out to you as well. When you talk about the relative deadlock freedom proof for M2, you will see that I got one part over here for ML. Let me just show to you. You can see this part over here is MLR1 guard, not equal to. This will be ML out 2 guard, where it is equal to. And symmetrically, similarly, you also got for the IL out guard, ILL1 guard, ILL2 guard as well, right? Let's talk about this one here. Given what we said before, because we know that the disjunction of this and also this one over here is really equivalent to true, right? There's one thing I want to say again. So this is not exactly right, not exactly true. Beg your pardon. The correct thing to say would be the Q here or not Q here, Q or not Q should be equivalent to true. So that means it would be as if we only got the original P. So the one to put over here should be P. Okay, maybe that's something you're wondering about. And again, the proof will be up to you. And we can easily simplify this particular goal over here to be just MLTL equals green. This also can facilitate the proof of the deadlock freedom because you don't really have to worry about two separate disjunction. They can be easily simplified into MLTL equals ring because we got exactly P and also not P. So that's really for the logical connection here. All right, so you guys got any follow up to this? So that'll be why we want to use not equal to as opposed to less than. Any follow up to this? You guys feeling comfortable about this? All right, I'll take silence as yes. Next one. Right, so this another question there on the Google Doc. I'm not too sure exactly what's being asked over here, but this is my interpretation. If that's what you asked, you can now speak up to maybe help me understand what you're asking. We are talking about invariant 2-3 over here, and I guess you just want me to explain why this is the case, right? A plus B less than D. I presume that's what you wanted to ask me. Okay, that will be my interpretation. If I'm wrong, you gotta let me know. This is one of the invariants for model M2. Let's see why it should be A plus B less than D. I would say a better way to understand this would be, think about if the traffic light is actually green. That means you may allow at least one more car to actually pass through from the mainland to the bridge. Right? That's informally speaking, because as long as if you shouldn't allow any more car to really pass from the mainland to the bridge, the light should be turned red right away. Right? So it's, the informal meaning is, if the MLTL is green, that means we should allow. Oh, let me not say we should. Let me say at least one more car. One more car can be allowed to exit from the mainland to the bridge. Right, that's kind of informal understanding. And how do we formulate this? This is how we do it. And if you if you can just some rewriting might help. You can think about A plus B less than D is really equivalent to A plus B plus 1 less than or equal to D. So the plus 1 over here is really that at least one more car that I'm talking about informally, right? You're saying that with whatever number of cars we have on the bridge and also in the island, we can allow one more car. And it's guaranteed, even after adding this one more car from the mainland, the total will still be bounded by the maximum, the constant that we declare in the initial model. Right? That's how I understand it. Alrighty, and that's it. That's all from the Google Doc. Any follow-up to this? Anybody? All right, so do you guys got any more questions? I mean, it's really your time. If you got more question, more than happy to answer. If you know, I'll let you go. Any other questions? I'll pause for a moment in case you're still formulating your question. Feel free. Okay, one more call. One more call. Any other questions? All right, I still got my office hour this afternoon at 2 p.m. Right? If you want to speak to me, feel free. All right. All right, guys. If you have no more question, that's okay. I mean, then I'll let you go earlier. Right? If you got further questions, drop by my office hour this afternoon, or I think Monday will still be fine, 2 p.m. as usual. Alrighty. All right, guys, you take care. And then I'll speak to you very soon. Right? Take care.